Welcome back to Bite-Sized Breakthroughs, the podcast diving deep into the latest research shaping the future of AI. Today, we're tackling a crucial challenge, making massive language models accessible and efficient for everyone. That's right, Alex. We're going to explore the world of 8-bit quantization, particularly for large language models, with our guest, Dr. Paige Turner. Welcome, Paige. Your paper LLM.int8, 8-bit matrix multiplication for transformers at scale, presents a groundbreaking solution for efficient inference in these colossal models. Can you give us a quick overview of what you've achieved?
Thanks, Alex. In essence, we've developed a new method for 8-bit matrix multiplication within transformer models that lets us run these models without sacrificing any performance, even when they have hundreds of billions of parameters.
That's a huge leap. Could you provide some context for our listeners, Paige? Why is this such a big deal?
Sure. Large language models, these massive neural networks, are revolutionizing NLP, from text generation to machine translation. But they have a major drawback. They're extremely memory intensive. For example, models with more than 6.7 billion parameters dedicate 95% of their parameters and 85% of their computation to the matrix multiplications within the feed-forward and attention layers.
So imagine you're a researcher with a modest GPU. You'd be hard-pressed to run a model with billions of parameters, wouldn't you?
Exactly. That's why we've been exploring ways to reduce the memory footprint of these models without compromising their performance. Enter 8-bit quantization. We can represent the model's weights and activations using just 8 bits, instead of the usual 16 or 32 bits, effectively halving the memory needed.
That's a pretty significant reduction. But here's where things get tricky, right? 8-bit quantization is notorious for degrading performance, especially with larger models.
That's correct. Existing 8-bit methods work well for models with fewer than 350 million parameters, but they struggle to scale effectively beyond that point. The problem is, as models grow larger, they develop these outlier features. These are specific dimensions in the hidden states that have extremely large magnitudes, far exceeding the values in other dimensions. These outliers wreak havoc on quantization accuracy, leading to significant performance drops.
So the problem isn't just size, it's the emergence of these outliers. How did you tackle that problem, Paige?
That's where our innovation comes in. We realize that these outlier features are both systematic and sparse. They emerge in almost all layers of the transformer, but they're concentrated in only a few specific feature dimensions. This allowed us to develop a two-part approach.
Let's unpack those two parts, Paige. First, the vector-wise quantization.
Right. Think of matrix multiplication as a series of independent inner products. We assigned separate scaling constants to each row of the input matrix and each column of the weight matrix. This is like having a finer-grained control over the quantization process, allowing for greater precision. We found that vector-wise quantization was essential for maintaining performance at scales up to 2.7 billion parameters.
So for smaller models, vector-wise quantization does a good job of handling the quantization process, but it's not enough for the giants of the AI world.
Exactly. For models exceeding 6.7 billion parameters, we need a more powerful approach. That's where the mixed precision decomposition comes in. We isolate the outlier feature dimensions and perform their matrix multiplications in 16-bit precision. This preserves the accuracy of these crucial dimensions, while the remaining 99.9% of the values still get multiplied in 8-bit, giving us significant memory savings.
That's a clever strategy. Basically, you're combining the strengths of both high-precision and low-precision computations, creating a hybrid solution for optimal performance.
Precisely. And the combination of vector-wise quantization and mixed precision decomposition is what we call LLM.int8. We tested this method on models up to 175 billion parameters, and it maintained full 16-bit performance in both perplexity and zeroshot accuracy, which are robust metrics for evaluating language model performance.
So Paige, it sounds like you've cracked the code for achieving efficient inference in large language models. But how did you actually test these ideas? What kind of experiments did you conduct?
We ran two primary sets of experiments. First, we evaluated language modeling perplexity on the C4 corpus using NVIDIA A40 GPUs. This helped us compare the scaling trends of different quantization methods, including our LLM.int8 method. We used a range of autoregressive transformer models pre-trained in FAIRSEEK from 125 million parameters to 13 billion parameters.
And what did you find?
The results were quite clear. Traditional 8-bit quantization methods, like ABSMAX, rowwise, and zero-point quantization, showed a significant degradation in performance as we scaled up. Their perplexity scores actually worsened with larger models. But LLM.int8 preserved perplexity across all model sizes, demonstrating its ability to scale effectively.
So it's not just about achieving good performance once, but about consistently maintaining that performance as you scale up.
Exactly. That's what makes LLM.int8 so powerful. It doesn't just work for a specific model size. It's designed to work for the largest models we can build today. We also conducted zero-shot accuracy evaluations on OPT models from 125 million parameters to 175 billion parameters using the Eleuther AI language model evaluation harness. Here again, LLM.int8 outperformed the baselines, showing no degradation in performance.
That's impressive. So not only have you solved the performance degradation problem, but you've also achieved modest speedups in inference for larger models.
Yes, that's right. Int8 matrix multiplication itself can be faster than 16-bit operations, but the quantization and decomposition overhead can offset those gains for smaller models. However, for models with a hidden dimension of 4096 or larger, we do see significant speedups, especially for those with 13 billion or 175 billion parameters. While our primary focus is on memory reduction, the performance enhancements we observed are an added bonus.
This is incredibly exciting, Paige. But as with any breakthrough, there are bound to be limitations. What are some of the challenges that still need to be addressed?
You're right, Alex. Our work has primarily focused on int8 quantization, which is currently the only 8-bit data type supported by GPUs. However, FP8, an 8-bit floating point data type, could potentially offer even better performance. That's something we'd like to explore in future work. We also need to investigate how our method scales for models exceeding 175 billion parameters. It's possible that additional emergent properties might emerge at even larger scales.
And what about the attention function itself? Did you explore using int8 for that part of the transformer?
That's another area for future work. We focused on the memory footprint of the model parameters, and since the attention function doesn't use any parameters, we didn't need to address it directly. But preliminary investigations suggest that we'll need additional quantization techniques beyond the ones we've developed to effectively quantize the attention function. And finally, we haven't thoroughly studied 8-bit training or fine-tuning. These areas are challenging, as there are trade-offs between quantization precision, training speed, and engineering complexity. We're planning to delve deeper into those areas in the future.
Paige, this is fascinating. It's clear that you've opened up a whole new world of possibilities for large language models. Now, to get a broader perspective, I'd love to bring in Prof. Wed Spectrum, who's been a leading expert in the field of AI and machine learning for decades. Wid, what are your thoughts on this research? Where do you see its impact on the AI landscape?
Alex, this research is truly remarkable. Paige and her team have made significant strides in tackling the memory bottleneck that has been hindering the adoption of large language models. This work has the potential to democratize access to these powerful models, allowing researchers and developers with limited resources to explore their capabilities. We're talking about models that were previously only accessible to tech giants with massive computational infrastructure.
So you see this as a critical step towards making these models more widely available and usable?
Absolutely. This could lead to a surge in new research and applications in LP and related fields. Imagine the potential for revolutionizing education, healthcare, creative industries, and beyond. The implications are enormous.
But Wood, there are always concerns about potential negative impacts. How do you see this work shaping the future of AI ethics?
That's a crucial point, Alex. We need to be mindful of the potential downsides. While this work makes these models more accessible, we need to ensure that access is equitable and that these powerful tools are used responsibly. The potential for misuse exists, So it's essential to develop ethical guidelines and safeguards to ensure that these models are deployed in a beneficial manner.
I think it's important to remember that AI is a tool, and like any tool, it can be used for good or for harm. The responsibility lies with us as a society to guide its development and deployment in a way that benefits everyone.
Absolutely, Alex. We need to have open and honest conversations about the ethical implications of these technologies. We need to invest in research and development that focuses on responsible AI, and we need to work together to create a future where AI serves humanity's best interests.
That's a powerful message, Wide. Paige, any final thoughts on the significance of your research?
We're incredibly excited about the potential of LLM-1 and 8 to make large language models more accessible and usable. We believe that this will accelerate research and drive innovation in NLP and related fields. We're also committed to addressing the ethical considerations associated with this technology. We need to work together to ensure that these powerful tools are used for good.
A powerful and important message, Paige. To recap, we've learned about LLM.int8, a groundbreaking method for 8-bit matrix multiplication in transformers, which dramatically reduces memory requirements without sacrificing performance. It addresses the challenge of outlier features that emerge in large language models, making these models accessible to a wider range of researchers and developers. This has the potential to revolutionize the field of NLP and impact various aspects of our world. But as with any powerful technology, responsible development and utilization are paramount to ensure that it benefits humanity. Thank you both for joining us today, and we look forward to seeing where this incredible research leads us.